Hello everyone, and thank you for attending today's webinar, NEMS Testing Challenges, Next Generation Ethernet, Packet and Optical Transport, sponsored by VX. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you today, we may follow up via email. At the bottom of the audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. Finally, an on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I'd now like to turn the event over to Heavy Reading's Principal Analyst, Optical Networking and Transport, Sterling Perrin. Sterling?
Thank you, Hannah. Hi, welcome everybody. Good morning and good afternoon. My name is Sterling Perrin, and I'll be the host and moderator for today. Topic, as you see, NEMS Testing Challenges, Next Generation Ethernet and Packet and Optical Networks, sponsored by VX. I'm joined today by Keith Cole, and he is Vice President of Product Marketing in the NEMS group within VX. Hi, Keith. Welcome to today's webinar.
Hello, Sterling. Thank you for the introduction.
Sure. Looking forward to it. I've obviously got a sneak peek at the slides, and it looks like some really interesting stuff going on in the world of Ethernet and testing, so looking forward to it. For everybody in the audience, the agenda slide should be up in front of you now. I will start the webinar presentation as I usually do with a look at trends and some of the challenges for the industry, really looking at it from the packet optical systems level, which is where I focus my research. And then I'll hand things over to Keith for the remaining bullets there, looking at optical module and form factor developments, a lot going on there. He'll walk us through Ethernet standardization developments, also quite a bit going on there. And then last but not least, as VX is a testing company, they've got quite a bit of expertise in what systems suppliers should be looking for in terms of testing all these new technologies coming to market. So he'll walk us through that. Should have about 10 to 15 minutes for Q&A, so please do ask away right through the webinar as they come to you. And we've also got 2 poll questions in this one, so be looking forward to your thoughts on a couple of the key trends that are of interest to us. Start with the drivers for the market, for optics, for packet optical. Clearly, it's the IP traffic growth. This is really no surprise. There are a whole new set of applications that are propelling traffic growth over the next several years. The bulleted ones list out some of the big shifts and trends we're seeing in traffic based on the Cisco Visual Networking Index modeling that they do. Generally, it kind of groups into applications around mobile devices of all sorts, around cloud, public, private, hybrid, and video everywhere. So that's the good news. The sobering side for the optics industry, which is where I focus, is if you look at the blue line, is Heavy Reading's, it's a set of historical data going back to 2010 and then our forecast out through 2020. And this is optical systems revenue, or on the flip side of that is optical systems spend from the service provider market, service providers of all types. And the reality is, while that orange line, and this is a normalized view of IP traffic volume, orange, blue is the Heavy Reading normalized optical spend. If you look at those two, you see the IP traffic volume growing 10x from 2010, where the optics spend is essentially flat. There's ups and downs along the way a bit, but if you kind of look at the long-term trend, it's essentially a flat market. And so what happens is then you get to the gray line. If you're mapping the optical spend per IP bit, there's a continual sharp decline in that value over time, dropping about 90%. So what it's saying is you're transporting more bits over time with the same amount of overall spend, and so the impact on the optical industry is greater efficiency is the essential requirement, not just in one point in time, but year after year, and expected to continue for sure. That's really the mandate of the industry. And so optics has met those demands. Clearly, it's been around since 2010, well before that. It's been through coping with that orange line versus the blue line for quite some time. It does this through a series of transitions. In fact, optical networks are always in a state of change and transition. I did host a webinar yesterday, and I focused on one particular transition in my intro to that one. That was coherent technology. Here I'm taking more of a holistic view of the broad set of transitions occurring across optical systems right now. So coherent is part of that, but it's not just about that. Really, you can sum them up as four different things. There's the migration from closed systems to open systems, one transition, from integrated systems to disaggregated, from in-house design to merchant-based wherever possible, and then from either fixed or monolithic systems to highly modular ones. Those are really the four things. If you look at the bottom left-hand corner, I call this the CFP-X module supplier evolution. This is the evolution for line-side optics, and it's essentially for many years the optics, the pluggable optics was on the client side, but your line-side optics were fixed into the system. The CFP form factor, when it came out, was, I believe, the first real form factor that could put high-performance line-side optics in the same form factor, and it's moved out from there, really contributing to the trends in modularity for sure, merchant-based to a degree, and also disaggregated and even open, kind of cutting across those things. I do call it CFP. As Keith will talk about the naming CFP, there's some other form factors that are coming into play. So it's really just the pluggable line-side optics modules and how they're evolving over time. That's the one we'll probably focus on most today in the webinar. Some other ones from a systems perspective to be aware of: merchant DSP is another huge change over the past couple of years. If you look at in coherent optics, the introduction of the digital signal processor was key development there. First, this was done in-house, but now there's a number of suppliers doing merchant coherent DSP silicon, which is really bringing that merchant trend along. In the packet optical side and in layer 2 switching and routing, we have the merchant network processing units. Broadcom and other companies have really propelled that trend along. I would say Arista is a very good example of a systems vendor that really capitalized on that trend to compete with companies that typically or historically had always used their own in-house ASIC design. Arista obviously has done very well in the data center and now moving out. And then last but not least is the move towards open APIs, common data models, and basically all trends around SDN. Also contributing across, I would say SDN would apply to open, disaggregated, and modularity as well, so cutting across a bunch of those. So the other interesting thing that's happening is while the models for systems design are in transition, the data rates for interfaces continue to scale to address the applications and capacity requirements across cloud, DCI, mobility, and video, as I talked about. One thing that became very clear over the past decade is that Ethernet's become the currency for those networking interfaces. If you remember SONET and SDH, that capped out at 40 gigabits. Then we moved to 100. It was a 100 gigabit Ethernet standard, and we're seeing the evolution from there. One very interesting thing that this chart, which comes from the IEEE, shows is the acceleration in standardization in Ethernet, which many may not be fully aware of. If you look back over the past 35 years, there were 6 rates standardized by the IEEE for Ethernet, going from 10 megabits to 100. And currently, and this is what Keith will walk through in some detail, there's 6 new rates being standardized all at the same time, which is pretty amazing and also, I think, somewhat confusing. So Keith will walk us through that. The other interesting trend here is that the data rates are scaling up. We're going to 400 gigabit Ethernet, but they're also scaling down all the way to 2.5 gigabits. I circled the ones that are of relevance for the service provider and data center audience that we have on this webinar, which is from 25 gig to 400 gigabit, which is what Keith will talk us through today. But it's scaling up and down, and I think it's really about efficiency. You want to really match your capacity and your power and the footprint to exactly what's needed for a particular application, and that's driving this whole proliferation of Ethernet data rates. The final point I'll make before I hand things over to Keith is that if you look at the network equipment manufacturers, the systems vendors that I've talked about, they're really among the first to get exposed to these new technologies. They have to verify them, test them, make sure everything works, and interoperability where needed before these go out and are deployed in the field. So with all these rates coming to standardization now really is the critical time for the equipment companies, and why this webinar is so timely at this particular time. So with that, let me hand things over to Keith. He'll go into a lot more detail across all those trends and talk us through the modules as well as the Ethernet data rates. So Keith, I'll hand it to you right now.
Thank you, Sterling. I appreciate the very good overview on the growth of the market and background information to frame up some of the discussions I'm going to have going forward. It's great speaking with everyone today. To provide some more detail on the technology side, one thing that is propelling the growth of these high-speed port rates is increase in high-density switching silicon. There have been many improvements in high port density switching silicon and routing devices such as ASICs recently. The first generation of these products was really based around 40 gig Ethernet ports with 10 gig SerDes or 10 gig high-speed lanes, if you will, driving data out to optical modules and to interfaces. Next generation was 100 gig Ethernet ports with 25 gig high-speed lanes, high-speed SerDes. Next generation was really going towards higher port counts of 100 gig, staying with the 25 gig SerDes. And where we are today and in the near future is 200 and 400G port rates, taking advantage of some of the newer technology for 50 gig high-speed lanes, 50 gig SerDes interfaces. Staying with this theme, one thing that is really making the growth rate of these new Ethernet standards accelerate is the reuse of these SerDes technologies. So for example, 100G Ethernet can typically use a 4x25 gig configuration for 25 gig high-speed SerDes or high-speed lanes. 400 gig Ethernet can in some form take advantage of 25 gig high-speed lanes. There's also standardization and process for 50 gig high-speed lanes. So there's a lot of common reuse in technology that fosters the growth in this area. Regarding optical transceiver modulation module advances, typically form factor really drives the optical transceiver market. The more ports that can be fit into a 1RU space, the better. And that's true mostly for data centers. There are some applications where signal integrity and reliability and some other factors come into play. But historically, the market's shown us that form factor is really based on port density. So speaking about 400G, the 400G optical transceiver module interface is going under quite a few changes at the moment. The first generation product is CFP8. This is the first generation pluggable optical module form factor. It's roughly the size of a 100G CFP2 module. This technology takes advantage of 16 25 gig electrical I/O lanes in the hardware, and it is PAM4 modulation capable on the optical side. The OSFP, or Octal SFP, is a more aggressive design as far as the packaging is concerned. It's a smaller footprint. This module takes advantage of 8 50 gig electrical I/O lanes and PAM4 on the optics side. The QSFP double density transceiver, pluggable transceiver, is interesting. In the market, at this time, it's thought that the QSFP double density will probably be the final package, and one of the reasons for that is due to its smaller size footprint. However, this module has the most R&D left, as it's the most stringent for signal integrity and cooling design concerns, packaging more technology into a smaller space and having to deal with the cooling and thermal properties. This module uses 8 50 gig electrical I/O on the electrical side and PAM4 on the optical side. What's very interesting about the QSFP double density, and also one of its main proponents, is the ability for backwards compatibility. So this QSFP double density port can also support a 100G, 40G existing QSFP modules. So there's backward compatibility potential using this form factor. And then also COBO, Consortium for Onboard Optics. This is not a pluggable optic, but rather a board mount optic, where the optics and the electronics are on the printed circuit board or PCA assembly itself, and the physical interconnect is brought out to the faceplate. This uses 8 times 50 gig electrical I/O and PAM4 modulation also. One interesting thing about this approach is that it really frees the faceplate space for a higher port density. It eliminates a lot of the thermal problems associated with having all this technology right at the edge of the faceplate and dealing with the thermal cooling. So there are many different optical transceivers that are in play right now to be able to support the next generation 400 gig Ethernet rates. From a 200 gig Ethernet point of view, QSFP56 is being targeted for this transmission rate. This form factor module is very similar to the QSFP double density, only it's maxed out at a 200 gig data rate. Sterling mentioned 50 gig Ethernet earlier. 50 gig Ethernet is being pushed towards the SFP56 transceiver, which is the same size as the SFP that supports 10 gig rates. Only this transceiver supports 50 gig electrical I/O and PAM4 on the optic side. And other modules such as QSFP28 that can take advantage of using 2 25 gig lanes and SerDes and combining them to be able to support a 50 gig Ethernet rate, allowing multiple ports on the same optical transceiver module. Then going to the 25 gig and 32 gig fiber channel port rates. The SFP28 is the module of choice here currently for those. It's the same size as the SFP, only this module supports electrical rates and optical rates up to 28G, allowing it to transport the faster 25 gig Ethernet and 32G fiber channel rates. And also on one of the introduction slides, there was mention of 2.5G and 5G base T. These, of course, are not optical transmission rates, but there's quite a bit of growth in this area, so I thought it would be interesting to discuss with the audience. These are copper SFP-based pluggable transceivers, or a lot of the switches and network equipment that natively supports these will be using the standard RJ45 interconnect. So even having said all of this, today the QSFP family of optics and SFPs are still the workhorse of the industry at this moment. There's a lot of discussion of the new modules of choice for 400 gig, 200 gig, and advanced rates. And typically what happens in the industry is after all the requirements settle, the market really starts to go to volume on the module that meets the majority of the requirements for most markets. High-speed port, Ethernet, and MAC rates. So 400 gig is really the highest speed Ethernet port rate that's being discussed at the moment. That's based on the IEEE 802.3 standard, which is planned to be released by the end of this year. It's the highest performance, most attractive price per port for very high bandwidth applications. 50 gig Ethernet is very interesting in that it provides greater port density and lower cost than 40 gig Ethernet. It's 5 times more bandwidth than 10 gig Ethernet in the same footprint. And then also 25 gig Ethernet, which provides 2.5 times more bandwidth than 10 gig Ethernet in the same footprint. 25 gig Ethernet is being discussed to be the next 10 gig Ethernet rate. Speaking on the 5G and 2.5G base T rates, as I mentioned earlier, these are RJ45 interconnects. What's very interesting point about these port rates is they're meant for switch-to-switch interconnects, where typically existing 1 gig electrical rates are used today. So by replacing the networking equipment in the switches and retaining the existing Cat5e cable plant, bandwidth rates can easily be upgraded. So it's a very powerful technology that allows increased bandwidth without having to change the existing cable plant. So we've discussed the new port rates, a lot of the new transceiver development and trends, and what does all this mean? Of course, all that technology is being rolled into next generation packet and optical-based networking equipment, primarily for switches, routers, very high-speed interconnects, muxponder and transponder cards in the packet optical networking industry, packet aggregation equipment and devices. So we're now up to a poll question.
All right.
I think the audience would.
Excellent. Yeah, thank you, Keith. So everyone should have the first poll question up in front. Keith talked about the next generation Ethernet rate, the high-end 400 gigabit Ethernet, and so we are wondering, for you, when do you expect service providers, operators to actually start deploying the 400 gigabit Ethernet rates? The standardization is, I think, Keith, you said it was that the one you said it was up for actually this month to be finalized as a standard? Is that correct?
Correct. The draft has been in place for a considerable amount of time. There are little changes to the standard, but it's expected to be completely approved by the end of this year.
So, okay, so coming now, so as a standard, and then when does it actually get deployed? In the next 12 months, so I guess we'll be looking at 2018. Within the next 13 to 24 months, so not 2018, but 2019. Is this something that you envision to be deployed in the next 3 years out or further, or if you're a bit skeptical and you feel the industry is good at 100 gigabit Ethernet or maybe the 200 gig standard, maybe there's no need for 400 gig at all. If so, click on that final option, never. Service providers don't need 400 gigabit Ethernet. Let me just give a second to get the kind of a critical mass here, and yeah, that's probably about right. Let me push it out here, and then I'll do a refresh. But here's what we've got right now, Keith. Hopefully you can see this as well. Looks like in the next 12 months, about 14%, but the expectation seems to be almost half, well, 45% in the next 13 to 24 months. And then after that, there's actually a pretty good groundswell of expectation for 3 years out. Is that where you would think it would lie, or were you expecting more deployments in the next 12 months?
No, I think the results of this poll question are as expected. We've been seeing a lot of early integration and development in the 400 gig space recently. I think it makes sense based on the new technology and the rollout of products to be seeing these advancements occur in the next 13 to 24 months in the majority. I think this is very in line with expectations.
All right, let me do one last push and get that. Yeah, it's held pretty steady. All right, great. So, yeah, with that, Keith, I'll let you continue on. I'll just put your next slide up here. You should be all set to go. Is the slide up?
Yes, we're set, Sterling. Thank you.
Okay.
So there are many challenges for product realization in this space. We've been talking about standardization and new technology, but bringing them to market, these new products, is something else. So there's a rapid pace of new technology, standardization in progress, much new technology to learn, multiple transceiver types, different fiber interconnect standards, multiple port rates and protocols, all being driven in a very quick time to market. So this challenges a lot of different teams, primarily in the network equipment manufacturing systems provider space, as those are the players that are developing and bringing product to market for the transmission rates. These areas include R&D labs, where new technology testing occurs, design verification, system verification and test labs, where real-world simulated environments occur, performance and interoperability testing, production manufacturing facilities, where rigorous test procedures are done to ensure that the products meet their documented specs before they're shipped, and also product demonstrations and systems integration. This requires traffic simulation and analysis and interoperability testing of the products. So to help meet a lot of these challenges of the industry, test equipment has to keep pace. So the next generation test equipment requirements need to be able to support these new standard port rates and protocols, also support the new pluggable optics and transceivers that we've discussed. From a piece of test equipment, it's very important that the test equipment itself can support the optical module that's being deployed in the network with native support, meaning no adapters in place. That allows the test equipment to actually be able to verify these transceivers in the test box itself and help segregate problems with that piece of hardware during testing cycles as opposed to problems with the optical side. It is interesting to note that traffic interoperability is supported between modules of different types. So for example, at 400 gig, using a CFP8 pluggable optic interconnected with a future QSFP double density at 400 gig, the traffic interoperability is fine between the two modules. That allows traffic verification from point to point. It just does not allow the transceiver module itself to be tested separately from the network. Also, another requirement is a solution designed to support testing from R&D labs all the way to manufacturing, providing a very high return on investment to companies who really need this new generation of test equipment to verify their products and services. And also very flexible and high-density traffic generation. This requirement is very common in most modern testing environments. The equipment really needs to be easy to use and efficient, allowing vendors and NEMs to focus on their products and services and not necessarily on the test equipment itself. Really needs to be a multi-user platform. Most equipment is shared in labs these days, so it's very valuable to be able to take advantage of sharing test instruments for different projects and different developments. It should support pay-as-you-go features to easily add new features, add new test port density, new rates, new protocols on the fly instead of having to be locked into buying everything at the onset with test equipment. And it really needs to support effective test automation. That really facilitates very quick time to market, test repeatability, which is very commonplace in almost every organization for automated tests of the new rates and technologies. So Sterling, I'll hand it over to you for the next poll question.
Okay, thank you. Everyone should have the second of our two poll questions up in front of you. And so the last question, we focused on the 400 gigabit Ethernet specifically. Here, we're more interested in, of all these different rates that are being standardized, what's the most important, at least in the near term. So which of the following port rates is most important to your organization over the next 12 months. And actually, this one is a multiple choice. So if there's more than one, you should be able to select multiple in this case. First, a 400 gigabit Ethernet, 200 gigabit Ethernet, N times 100 gigi, N times 50 and 25 gigabit Ethernet, and then the 2.5 5G base T, the copper ones that Keith gave some explanation of, and then 32 gigabit fiber channel. So 1, 2, 3, 4, 5, 6 different options. Again, you should be able to select more than one, and we'll see. Just take a look and see how many folks we've got coming in here. And when we get enough, we'll push out. Question while we wait, because I want to make sure we get enough people responding. You know, the compatibility on the different form factors. Is there an expectation of one? You know, like if you look at 400 gigabit Ethernet in particular, it looks like there's multiple different options being put there. Is there an expectation of compatibility across the different modules, or is it just one module would be compatible with another? What's the level of standardization expected there?
It's a very good question, Sterling. Yes, compatibility should occur. It's expected to occur as long as the physical interconnect is the same technology, the same reach, if you will, say an LR8 on one module side versus an LR8 on the other module side, you know, 10 kilometer type interconnects. There is an expectation for the modules to be interoperable with each other.
Okay, well, I guess that makes sense, because otherwise you're making a lot of big bets that everyone's going to do the same thing as you. Good. So the
Absolutely.
results are yeah, go ahead.
I was going to say it's very similar to today's 100G market with CFP2, QSFP28, CFP4 transceivers. They are different form factors, but from a data interoperability point of view, they're very, very compatible.
Okay, good point. And the poll question results are up. I'll do one more push, but I think we've got a good number in. So you had pretty resounding results, 62% almost N times 100 gig E. And then the rest of them are almost all in line, except for the 200 gig E, which is lagging. Again, is this from your interactions? Is this what you were thinking would happen, or any surprises in this data?
There are no surprises here. I think we'll continue to see increase in 100 gig deployments, the need for 100 gig interconnects, and then also 400 gig to help support the very high bandwidth requirements in data centers, data center interconnect. So I think these results are very in line with expectations. There's a lot more talk in the industry about the high-speed 400 gig interconnects compared to 200 gig at this moment. That could shift at any time, of course, but it seems very reasonable. Then also transitioning down to the lower speed rates, such as 50 gig, 25 gig, 32 gig fiber channel. I think these are all in expectations. Where we see growth across the board, but more focused on the 100 gig delivery, 100 gig interconnects.
Good. Yeah, and with that, we'll let you go on and get into some of the, I think, the more specific testing requirements. So your next slide should be up.
So another requirement is flexible high-density traffic simulation. So test equipment really needs to be able to generate and analyze high-density and aggregation applications. So what I mean by that is generate 400 gig test capabilities, as well as lower speeds such as N times 100 gig, 50 gig, 25 gig. Most of the testing that occurs in SVT verification labs, real-world simulation, requires a test box to be able to generate traffic at these different rates. For aggregation purposes, transponder, muxponder type testing, it's not very often that just one rate alone is used for test applications. Also, multiple protocol support for multi-service test applications. For the most part, we've been speaking about Ethernet, 400 gig, 200 gig, some 32G fiber channel. But today's teams, especially NEMS, R&D labs, production and manufacturing, are dealing with a lot of different technologies and products. So a good requirement for test equipment is to be able to service and meet the test needs of all these different protocols with the same piece of test equipment, instead of being locked into one piece of gear for each independent technology. A large part of the verification process for these new technologies is actually verifying the transceiver module itself. And I mentioned something about this earlier. Being able to support the same transceiver module in a test set that's used in the deployment is powerful. That really allows engineers to verify the performance of that transceiver independently from the network. They can verify the bit error rate performance, the optical power levels, the output power, received optical power, the programming of all the internal registers in those modules, and the MDIO and I2C to verify the health of the module, that the read-writes to the module for programming works effectively. Verifying the input tolerance to power levels, the module power consumption itself to make sure there are no internal problems. And also verifying the high-speed lane clock and the line frequency measurement to ensure that the line interface rates can handle a wide variety of line frequency and clocking rates. Forward error correction is also very important. A lot of the newer rates that we have been discussing, such as 400 gig Ethernet and 32 gig fiber channel, for those, forward error correction is mandatory. It's no longer optional just for the short range or short distance interconnects. Forward error correction is really a means to ease the electrical and optical design characteristics of some of these new port rates, essentially lowering power and cost. But with that comes another layer of testing that needs to be accomplished by test and R&D teams, and that's to verify the proper performance of the FEC or forward error correction layer. What's really important here is verifying the pre-FEC bit error rate, the bit error rate of the line that occurs before the FEC kicks in and starts correcting errors. The post-FEC BERT is really the bit error rate that occurs after the FEC layer does its job by correcting the errors. And also another part of this is being able to manually simulate line errors, causing FEC error generation and corruption. And this is required for network equipment vendors, device vendors, to simulate these errors on the line to ensure that FEC receiver designs, whether they're in an ASIC, a network element, or some software trigger based on a FEC error threshold, are working properly. You need to be able to generate errors pre and post those thresholds to properly verify those conditions in the network devices. So we've been talking about different port rates, different speeds of Ethernet. However, testing at the Ethernet IP level for traffic verification is still constant. It's still the same similar tests that need to be run at 100G and 10G rates, only now for faster rates such as 400 and 200G. That involves traffic simulation and measurement, throughput, frame loss, BERT, latency and jitter measurements on the traffic, verifying the frame size, MTU performance of Ethernet IP data, running the RFC and Y.1564 compliance tests, and also verifying network response to invalid traffic conditions. The instrument needs to be able to verify and generate negative test cases so engineers can verify the equipment correctly responds to those conditions. And also verifying the PCS layer. The PCS layer for rates such as 100G Ethernet, 400G Ethernet take advantage of multiple high-speed lanes all aggregated together to form a larger data pipe. And the time difference due to latency or skew on those lanes needs to be verified. The lane alignment and lane swapping process, the protocol layer that deals with combining those lanes needs to be verified, as well as error and alarm response and threshold testing. The ability to generate errors and alarms, verify errors and alarms coming back from networking equipment. From a fiber channel point of view, fiber channel still needs to have throughput, frame loss, bit error rate tests, latency jitter type of measurements to verify the frame data. However, for fiber channel testing, it's a requirement to have switch fabric and port login capability if you're sending data through a fiber channel switch. Fiber channel is a connection-oriented protocol, unlike Ethernet, so it requires a dedicated connection to the switch port before traffic can be passed. So it's very important that instrumentation supports this login capability. And also to be able to verify the buffer credits and the flow control aspects of the interconnects. Service disruption time measurement is also another critical measurement that needs to be considered when verifying the products for these next generation port rates. Service disruption time typically in the past really meant verifying that service level agreements are met for switch restoration, automatic protection switching for the typical SONET SDH interfaces, although it's very valid for all the different port rates and protocols. By verifying service disruption time measurements, that allows vendors to prove out their microcontroller firmware designs, clock data recovery circuits, and the reset times that are associated with these components. For example, if there's a loss of signal in the network and the optical line switches over or another piece of gear needs to take over for that time period, if there's a fiber cut, events like that occur, restoration switchover times in the network. And it's very important to be able to verify the end-to-end disruption time of these devices. So if you're verifying the measurement at a service level, the end-to-end measurement is very critical. However, it's also important to be able to take measurements for every device in that chain because all of those times add up and provide a cumulative service disruption measurement. So taking that time in a transceiver module and also, say, in a network line card, isolated from one another are very important to characterize that overall performance. And also signal integrity testing. We've been speaking about Ethernet IP layers, but for those who are involved in IC development, devices, FPGAs, PCBs, it's very important to get an overall feel of the signal integrity of those hardware devices. So typically layer 1 unframed BERT testing is used for that. It's a very simple PRBS test to generate and analyze signal integrity on those devices. Being able to modify and measure the high-speed lane clock is very important. And also equalization, being able to verify the electrical signal level tolerance and margin in the IC's transceivers is also another important test for verifying signal integrity. So this is an example of an instrument that provides the majority of these features that we have discussed and these requirements. A true multi-port instrument, being able to generate mixed traffic rates from 400G, 100G, 25G, different transceiver types, CFP8, SFP28, QSFP28, really a very flexible system that allows growth and individual modules to be added to the field as port density increases, controlled by a remote user interface, test automation, very modular platform that fits in with the modern testing environments and network equipment manufacturers' labs and facilities and in production floors. So in summary, there are a lot of new rates, new networking equipment, transceivers, really challenging the industry, especially in the test and measurement divisions. And there's really a heavy burden on R&D and testing organizations to make the products right. I mean, no one's really expecting products to be released that are full of bugs or do not have the correct bit error rate tolerances. So it's very important for full characterizations of these systems before they're deployed. And with the new technologies, the new rates, most existing test equipment toolboxes really need an update to support these new applications, to support the new transceivers, the new line rates, and successful delivery of the next generation products. So with that, we'll go ahead and take some time for additional questions that the audience may have on the discussions we've had today.
Yeah, thank you, Keith. Great presentation, covering all the new form factor activity, covering all the new Ethernet rates coming out, and then getting into some of the test requirements. So we covered a lot of ground. We do have at least 10 minutes for Q&A. We've got some questions here, but this is definitely the time to ask some more, and we'll get to everyone we can. In the meantime, let's start. Question. When you reference the 50 gig electrical I/O input-output for optical modules, is this NRZ or PAM4 signaling? And maybe also explain out, as you answer, NRZ versus PAM4, what's the fundamental differences there?
Sure, very good question, Sterling. The electrical interface, when it is 25 gig to the transceivers, is an NRZ interface. When it is 50 gig, that's referenced as a PAM4 signaling. So effectively, it allows more bits to be transferred in the same amount of time. A very high-speed interface to the transceiver module. It allows us to push the high-speed boundaries of these optics even further.
Okay, and just the distinctions for people that may not know, NRZ versus PAM4, if you can explain that out a little bit as well.
Sure, there are different modulation schemes used to modulate the data over time. NRZ compared to PAM4. PAM4 is a newer technology. It allows more data to be modulated over the same period of time. The frequencies stay the same, but more data can be conveyed and communicated in that same period of time.
Okay.
So it really challenges the optical side, becomes very important when you start talking about FEC analysis, optical performance. That area is really key to be validated when you start using PAM4 modulation schemes and signaling with some of these next generation products.
Okay, excellent. And another question, the QSFP double density, can optical modules such as QSFP double density also support the 200 gigabit rates? I think you presented them in terms of 400 gigabit E.
So that's a very good question, Sterling. The QSFP double density port is going to be standardized to be able to support QSFP double density modules for 400 gig communication, and is also backwards compatible with QSFP56 modules that are designed for 200 gig, and also the QSFP28 QSFP Plus generation. The connector is such that there are two actual electrical interconnects. Two connects are used for 400G, and one connect is used for the, I'm not going to say legacy, but the existing QSFP28 and QSFP Plus modules. So it's a very flexible port. That's one thing that's gaining a lot of traction with that port format.
Well, let me ask a follow-on question to that. Just was kind of inspired by the poll results on the second. The 200 gig got the least amount of interest, at least in this particular group. I'm wondering, what are the advantages do you see of going to 200G versus as opposed to the 400 gig? I mean, is there a major, what are you saving a lot on power, or it doesn't seem like it's a footprint issue? Or is it a cost of the modules going to change dramatically? Just curious on that.
Yeah, I think all of those come into play, and it's also a form factor density. If systems can support 400 gig bandwidth in the same form factor, same interconnect as they can 200 gig, for a lot of applications, it probably makes sense to go ahead and have the 400 gig interconnect. 200 gig is one of the stepping stones that, can be used as an interconnect depending on the requirements for bandwidth. But I think all of the items that you mentioned come into play as far as that's concerned.
Okay, right. I made the comments in the beginning about just getting all the requirements right-sized to the exact application. So I guess it kind of fits that trend to have it close to what you need as possible. Question, let's see. Yeah, I guess for 400G, what kind of fiber will be used? It looks like single mode or multi-mode, I think, if I'm reading the abbreviations correctly. Does that question make sense to you?
It does, and that will really depend on the transceiver technology. For 400 gig, there are long-range interconnect standards, LR8, which is using eight lanes of 50 gig PAM4 modulated data. Those are typically running on single mode fiber, and there are also standards in place for shorter interconnects, which will take advantage of multi-mode fiber applications as well. Very similar to the 100 gig market today, where there are 10-kilometer reach modules, 100-meter reach modules, just to right size to the application and reach that is required for those interconnects.
Right. So similar to my understanding, multi-mode was shorter reach fiber, usually within the building, and single mode it tends to be pretty much most of the world ideal in the telecom industry. Is that similar for the 400 gig? If it was 400 gig in multi-mode, is it what? Do you have a sense of what kind of reaches those are? Is it pretty much within the building? Is that?
So yeah, and there's a new DR4 standard that's being talked about, which I believe is a 500-meter interconnect.
Okay.
That's another different reach standard. So the transceivers and their reach is being right-sized to the market requirement, if you will. So
All
vendors
right.
do not have to provide higher cost modules for overkill bandwidth and reach situations.
All right, and then this one is quite technical. You'll have to explain out the acronym here. At least it's not one that I'm familiar with. I have heard about the SSPRQ pattern being a must-have for SI, I'm guessing systems integration level testing of components. Can you elaborate? Hopefully you understand that question. If you can explain out SSPRQ.
Yeah, there are some unique test patterns such as SSPRQ that are called out in the standards for validating some of the very low-level signal integrity testing, very specific for verifying test patterns, signal integrity levels, different modulation schemes, a little bit more deeper than an unframed PRBS test pattern. Those are very hardware-centric test patterns, if you will, to verify the low-level electronics are correct. Those are not test patterns that would typically be used in service delivery tests, production and manufacturing. Those are used at very low-level R&D, design-level type test environments.
Okay. R&D, that probably explains why that one hasn't popped up on my conversations pretty much ever. Okay, glad you knew that one. Yeah, a question specific to test. Can test equipment use the same pluggable transceiver as the network, and what are the benefits of doing that?
Yes, it can. I briefly touched on this earlier during the presentation. There is a benefit for the test equipment to use the same pluggable transceiver as operators and providers are deploying. And one of the main reasons for that is being able to verify that transceiver independently of the Ethernet link. So for example, that transceiver can be taken out of the port of the network blade or even tested before it is deployed internal to the test equipment with a loopback fiber to really verify that module itself performs correctly before it's deployed. And that's very important to be able to help segregate any network problems, whether they're related to just that pluggable transceiver module or whether they're related to some other interconnect or network card type of condition.
Okay, good explanation. So for the audience, there should be a poll pop-up link on your screen. If you can take a moment to fill that out, and we'll gather up that feedback, and it helps us with our webinars. So please take a moment to do that. We probably have time for maybe 2 more questions. There was a question that came in. If the person is still on, I might just, if you could clarify. The question is device compatibility with cloud and virtualized networks. I wasn't quite clear if they're talking about the particular test equipment or if you're talking about the modules that were described. It seems to me that this person is leaning towards the test equipment, but I'm not sure. I don't know.
Well, I'll take a stab at that question, yeah. Sterling. I think, to answer that, what we've been discussing, the next generation Ethernet and even fiber channel rates are more of a data communications type interface. They provide the high-speed data interconnects to be able to support the cloud or virtualized environments. The data that's being run in a virtualized environment or in a cloud application is really carried over these high-speed interconnects between equipment. In the test equipment examples, some of the challenges that I've been discussing are really geared towards the development and release and manufacturing of the port rate equipment, the physical 400G, 200G, 50G type communications interconnects. Not necessarily geared towards the virtualization and cloud application layer testing requirements.
Above it, right. I think we got time for one last question, and then we'll have to close out. But are modules such as CFP8 designed to support other rates than Ethernet, with the example of such as OTN transport? And maybe explain, I know we had some slides in there earlier, you may have cut them out around the role of OTN transport as well. In this
sure.
Yeah.
Let me see if I can go to one of the slides. It's very close to this topic. One thing that's to note is most of these new port rates and transceivers are geared towards Ethernet. CFP8, for example, is geared towards 400G Ethernet rates. The QSFP28, CFP4 market, even CFP2 market today for 100 gig, those modules can be geared for either 100 gig Ethernet or they can support multi-rate, OTN transport, and Ethernet. Today, the new generation of products such as CFP8, QSFP double density are being really strictly geared towards the Ethernet IP generation rates and not necessarily the OTN layer.
Okay, with that, we're pretty much at the top of the hour. I think we got to a lot of questions, so thanks for everyone for asking them, and thanks, Keith, for running through all those. If there's any additional questions we haven't got to, I think VX may follow up with you individually. But with that, I want to thank Keith and VX for sponsoring and participating today, and thanks to everyone in the audience for listening in and for your great questions. Goodbye, everybody.
Thank you, everyone. Thank you, Sterling.
You're welcome.